we've reached a mysterious period of time, 12.5 billion years ago.
There's this time period that we can't see because nothing's formed yet. It's this epoch that's called the Dark Ages.
During the Dark Ages, the universe was a very different place than the one we live in today. It's filled with dense clouds of hydrogen gas. Just as gas obscures stars in the Milky Way today, these clouds of hydrogen block the view inside the early universe.
It's extremely frustrating because this region, this time period, holds within it, in some sense, the Rosetta Stone of galaxy formation.
But there is one clue to what's happening inside those dense hydrogen clouds. Look back further in time to a moment just 380,000 years after the Big Bang. The universe isn't filled with darkness, but with light. Its faint afterglow is still visible to astronomers today.
In fact, this picture is amazing. This is a picture of the early universe. This is an image of the afterglow of the Big Bang.
The universe is filled with a hot atmosphere of matter and radiation. But already the seeds of change are being sown.
Everywhere we look around us in the universe, we see structure. We see galaxies all over the place. Where do these galaxies come from? There's a big clue to this buried in this picture. If you look closely, you can see that there are red spots and there are blue spots. These red regions are regions where there's basically more stuff. And the blue regions are the regions where there's less stuff.
This image reveals tiny variations in the density of the gas that fills the early universe. Minute ripples that will grow with time.
We think that these ripples, these primordial ripples, are the seeds to all future structure. These ripples eventually grew into what became the first galaxies.
It takes a powerful force to grow something so small into something so big.
It's gravity that amplifies these ripples. And in fact, we need an additional source of gravity to amplify those ripples to form galaxies like we see today. And that additional gravity comes in the form of dark matter.
What happens is that first the dark matter forms the structure. The ordinary matter then follows the dark matter. The ordinary matter is hydrogen and helium at this stage. And the hydrogen and helium fall to the center of the dark matter halos that are forming, and that's going to become the galaxies.
Dark matter may be the missing link between these minute ripples in the early universe and the vast cosmic web that now fills space. But dark matter is invisible. So there's no way to actually see it creating the cosmic web. But the process can be simulated in one of the world's most powerful supercomputers.
Here we are at NASA Ames, the research center where we have the Pleiades supercomputer. Each one of these cabinets contains 512 processors. Let me show you. So that's half a terabyte in each one of these cabinets. There's 110 of these cabinets to make up the entire Pleiades supercomputer. So this is a really big supercomputer. This is NASA's biggest.
The challenge is equally big: to develop a virtual universe from its early beginnings all the way to the present day, to see what role dark matter might have played in shaping the cosmos. If you tried to do this on a home computer, it would take over 680 years.
If we're doing our job right, we can put the pictures into a video, if you like, that shows the whole structure of the universe.
And this is the end result. It's called Bolshoi, an amazing visualization of what the structure of dark matter might look like in the universe today.
So what we're looking at is a region about 200 million light years across, which is actually just a small part of our really big simulation that we call Bolshoi, which is Russian for big. Everything that you see here is actually completely invisible. It's not the visible universe that you're seeing. The bright spots are dark matter. They're the halos of dark matter within which galaxies form. And each one of these little blobs would represent probably one or at most a couple of Milky Way-sized galaxies. And you can see that the galaxies are in long chains, filaments we call them. Basically, all the structure is forming along these filaments of dark matter.
Now comes the real test of success. Premack compares the Bolshoi predictions with the actual structure of galaxies scientists see in the universe.
As far as we can tell, these simulated universes that we make in the supercomputers look just like the observed universe. There don't seem to be any discrepancies at all. This is exactly the way we see the galaxies distributed in the observed universe.
The Bolshoi simulations are astounding. They match the pattern of galaxies seen in the cosmos today perfectly. It's persuasive evidence that dark matter has been sculpting the universe for billions of years.
Now, I'm really impressed with this because we stuck our necks way out when we made these first predictions, and they turned out to be right, and they keep turning out to be right. And this is of course great joy for a theorist.
By going back to the beginning of the universe, astronomers have uncovered the origin of the underlying structure of the entire cosmos. But our time travel is far from over. The question of how the first galaxies kindled the very first stars still remains. We're taking the Earth inside the Dark Age. A time over 12.5 billion years ago. The sight is spectacular. Our skies are lit by the first stars of the Milky Way. They're like kisses the hydrogen fog, bathing the Earth in strong ultraviolet energy. These first stars will change the way we see the universe forever. Tom Abel studies the life and death of these early stars.
The beautiful thing is that we now have computers. We program them with the laws of physics. Put in some gravity, hydrodynamics, how gases move around, some of the chemistry. And as we evolve it all together, we gain an intuition of how stars come about. And in the case of the very first stars, this is absolutely crucial.
Abel begins with the basic ingredients available during the Dark Ages: hydrogen, helium, dark matter, and gravity. Using computer models, Abel recreates the lives of these early stars.
Here we see one of the first stars in the universe. It's 100 times as massive as the sun, 1,000,000 times as bright.
The first stars are huge, swollen by the massive amounts of hydrogen gas pulled in by the gravitational force of dark matter.
And so even though they have all this fuel to burn, you'd think they could live for a long time, they run through it so quickly that even after a few million years, they're already dead.
The first stars in our Milky Way are fierce, high-octane stars, burning their hydrogen fuel at tremendous rates, racing through their life cycle.
They like the rock stars. They live fast and die young. They run through that fuel very quickly, and even after just a few million years, they already die.
They die in some of the most violent explosions ever to rock the universe. Gigantic supernovas that shine brilliantly. The energy given off during the life and death of these massive stars leads to a miraculous transformation.
In the first billion years of the universe history, galaxies start to form in a dark hydrogen fog, their light not being able to get to us. But as time progresses and their most massive stars put out ultraviolet radiation, it's that radiation itself that changes the fog around them. And the universe becomes transparent in those regions. These galaxies in here clearing out the fog around them.
The blue voids are where energy from the new stars is clearing the dark hydrogen fog.
But towards a billion years after the Big Bang, the entire fog has cleared, and we now see all the galaxies and their dark ages end.
As the hydrogen fog lifts, we get our first glimpse of newborn galaxies, including our very own Milky Way.
This remarkable image is the Hubble Ultra Deep Field. It's the longest exposure that's ever been taken with the Hubble Space Telescope. It's a truly remarkable image, probably the most famous to professional astronomers.
For over 11 days, Hubble pointed at a tiny patch of sky, about the width of a dime, held 75 feet away. Every faint smudge of light is a galaxy. For Richard Ellis, it's a treasure trove.
So much like an archaeologist would piece together history by digging into deeper and deeper layers, so a cosmologist like myself uses this image to look at the history of the universe, how the most distant galaxies, seen as they were a long time ago, evolve and grow to the bigger systems that we see around us today.
This image gives us a sense of the dawn of our Milky Way.
When we look at these early galaxies, they don't resemble the star cities that we see today. They're lumpy, they're irregular, they appear to be interacting with their neighbors, they're physically very, very small. So clearly the universe was very different in those early times.
12 billion years ago, the universe is a much smaller place. It hasn't yet expanded to the size it is today. Our young Milky Way is jostling for room.
So it's very difficult for these early galaxies to establish themselves. These early galaxies are struggling to survive at this very early time.
It's survival of the fittest. The largest galaxies grown bigger by devouring the smallest.
So it's tough for these early systems to form, but clearly they do, and they eventually merge with their neighbors and form the bigger systems that we see today.
These collisions in the early universe created the beautiful spiral galaxy we live in today. And they've never stopped. Astronomers believe there's still one final collision in store for the Milky Way. one that will change it forever.